And next we have Ilaria Pascucci, and looks like her talk could have been the whole conference or the whole workshop. So please take it away.
Yeah, thank you very much for the opportunity to talk about. Can you hear me actually? No? Yeah, now it's on. Okay, all right. So thank you very much for the possibility to talk about this topic, which I'm really passionate about. And so I want to start by telling you why I think it's important to carry out demographic studies across stellar mass and time. Then I want to briefly summarize what we are learning. Unfortunately, there are only 25 minutes, so I have a few selected results that I will be highlighting, but there is much more. And then I will conclude with a slide looking ahead about the missions that are available and what we could learn further. So first of all, on the motivation, I want to start with this, let's see if it plays. Oops, we go back. Oops, it typically plays. Wow. Okay, so I guess we'll do it without showing the animation. But essentially, this is a screenshot of what could have been an animation of the results from the Kepler mission, which shows the diversity, essentially, of planets and also planetary systems. So the sizes of these circles scales with the sizes of the planets, and then you would have seen these planets orbiting around, which is really nice. But in this case, you can still see the diversity of orbits and orbital architecture. So yeah, I think it says it's not allowed. That's the reason. I think it's okay. We can move to the next slide. It's fine. So when you look at that type of diversity, the question is really, what are the key physical processes that shape this diversity? And throughout the workshop, you have heard already of many physical processes. Here I'm listing just a few, and I have grouped them in two big boxes. First, initial conditions related to planet formation, so diversity of disk properties, diversity of processes related to formation, orbital migration, and then we have a number of processes related to post-formation, the evolution. So I want to motivate the reason why you want to look at observation covering a large range in stellar masses by looking at this first box, at the planet formation, and in particular to the disk property, something that I've done quite a bit in the past. So here at the moment is an empty plot. You have the mass in solids, and here you have the mass of the central star. And what I'm going to show you next are data points from the Atacama Large Millimeter Array covering this large range in stellar massing and showing what is the amount of solids in young disks within which planets are going to form. So this is a log-log plot. So to orient yourself, this is one Earth mass. Then on the top here is 10 times the Earth mass, so you can think about it as the cores of the Jupiter, for instance, and up there is the mass in solids in our solar system. On the x-axis, these are the type of stars we are talking about. So here is where the FGK would be. There is where the M stars would be. So you see, if you want to cover an order of magnitude or more in stellar mass, you definitely want to observe your M dwarfs. So now I'm going to remove this rectangle here, and you can see the data points. The circles are detections, the other are upper limits. And only when you go down to the very low mass stars, when you go down to the brown dwarfs, as we could do here, then you start to see an important correlation between these two quantities. In other words, there is at any stellar mass a large range in disk solid mass, but then by using the mass as a leverage to discover these trends, you see that more massive stars, stars with disks that have more solids, and lower mass stars have much less. Yeah, I also want to advertise this recent result that we have. This is a large ALMA program over 100 hours. What I've been showing in this plot is only the mass in solids, but now, as a few weeks ago, we also got out 12 papers on this large program looking now at the gas evolution around sun-like stars. So not yet as a function of stellar mass, but still very interesting. Now, why do we want to look at the evolution aspect? So I'm going to show just a plot here, but to make the point. So what you see here is planet radius as a function of period, and then these gray regions are density contours for the old, billion-year-old Kepler population. So now, if you look instead at the young objects, which are plotted here on the top, and in particular, you can look here at the stars, you see that this young population occupy a region in this plot that is quite different from that of the old population. So there is something here to learn in terms of evolution, and that's why you want to do demographics as well as a function of time. So I will be showing that later. So now let's start on what we have learned so far. So first of all, I will be talking about different types of planets. So I want you to have this figure here to highlight which type of planets we will be discussing. This particular one is from the Kepler. So each of these points is a Kepler transiting candidate exoplanet. And so we'll be talking about the hot Jupiters, giant planets close in, warm giants there, and then the smaller planets. In particular, I like this plot because it shows already what are the occurrence rate, the intrinsic occurrence rate for this type of planets. And there is also a tool that you can use, which is called EPOS, which we developed at the University of Arizona, that you can use to calculate intrinsic occurrence rates. It's quite easy to use. I will not be talking only about transiting exoplanets. We have seen already many times this plot, but it's important because it highlights the complementarity of different techniques. So now in green here, you have the radial velocity planets. And in purple, you have the transiting planets, other color for other techniques. We have heard all today of the complementarity. And that's why we also had the hands-on session yesterday afternoon, because it's really the time to integrate information from all these different techniques. So let's start to look at what we are learning about giant planets across stellar mass. So here is a plot of giant planets occurrence rate for the hot Jupiters. We have observations from TESS that are in purple and also from Kepler in other colors. And so what you notice here, oh, it's out? Oh, right. I hope you could hear me, or I was shouting enough probably. So what you can see here is first an increase in the occurrence rate and then a decrease. But again, this is the hot giant planet population. Let's now use radial velocity to look at planets, giant planets that are further out. So same thing, first an increase towards higher mass and then a decrease. If you look carefully at these plots, you might notice that the peak of the distribution is not exactly at the same stellar mass. I'm not going to comment on that, but I want to comment on why we think we have this first increase and then a decrease. So first here, looking at occurrence rate towards the lower mass stars, this trend could be well due to the fact that we have less solids in the disk to start with. And this connects to the previous figure that I've shown you. Regarding the decrease towards the higher mass stars, this could be also due to disk properties, in particular to the observation that gas in disk around more massive stars disperse faster than around lower mass stars. So both of these trends may be due to initial condition in the disk and how this property scales with the mass of the central star. Now, let's look at the smaller planets. I'm going first to group all of them, the sub-Neptunes and the super-Earth together, and I want to see how they look, the occurrence look as a function of stellar mass. So this is the occurrence in this specific period from Kepler 2 to 50 days. It's a function of radius of the planet, and one thing we noticed already early on was that there seems to be an increase of small planets towards lower mass stars, which are here indicated in M dwarfs, and they are in blue. Now, fast forwarding 10 years, you can do this type of study. You can extend this type of studies to the more massive stars. So here, now we go from G, F, and A type stars. Again, number of planets as a function of planet radius. And you can see overall through these studies, as well as others indicated above, that the M dwarfs, so the smaller stars, seem to have more small planets than higher mass stars. Again, these are transiting planets, so relatively nearby. And when I say small, I mean less than 2.5 Earth radii. I'm not going to talk more about M dwarfs because there is a dedicated presentation on Thursday, but I want to make a connection again to the processes that may lead to this observational result. So why do M dwarfs have more small transiting planets? So we heard about, in previous talks, about different ways you can form planets, different theoretical models. And so here, just for brevity, I want to illustrate the pebble accretion model, which seems to explain some of these trends. So more information from the talk of Christoph Mordassini and also Ivli, but pebble accretion in a nutshell needs pebbles, so it needs these small grains that we are able to detect with ALMA to move inward and increase the amount of solids to then form quickly the planets. I took this sketch that is for the solar system because it also shows that if you have a giant planet in between your pebbles and the inner part of the disk, then your pebble may not be able to cross and you may not be able to form your super Earth and sub-Neptunes in time while there is this gas around. So this is, for instance, how this paper explains the observational trends. And so just to summarize here the trends, you have on this side, so now this another trick here. On this side, you have the observations, Kepler observation showing that there are more smaller planets around small stars. And on the bottom, instead, you see a trend of fewer cold giants around small stars. On the other side of the plot, you see the theoretical models and the outcome of those models. In particular, you see that if you don't have here any giant planet in your simulations, then you would tend to predict more sub-Neptune and super-Earths around more massive stars because you do have more solids in your disk. So to get this trend of less small planets around more massive stars, you need to include these giant planets. So you need to have some filtering of the pebbles from the outer disk to the inner disk. So there are also some important predictions of these models. First of all, you see here that this predicted curve turns over towards the very low mass stars. So one prediction is that you would have less small planets as you go towards 0.2, 0.3 solar mass stars. And there is a poster that you can check using the K2 data that is already probing that turnover. And then another prediction of not just this model, but more generally of the pebble accretion model is that you should see kind of an anti-correlation between a presence of an outer gas giants and your sub-Neptunes and super-Earth. There is a lot of literature about that. It seems like more data would be necessary. What I cited there is just one of the most recent, so you can find papers, so you can also find more references inside. There are other observations using demographics as a function of stellar mass, showing that pebble accretion might work. I don't have time to discuss them, but they are cited here, and the main point is regarding the scaling of the typical mass of the planet as a function of stellar mass. Now, so far, we have looked at the occurrence in certain period or semi-major axis being across the stellar mass. But now what if we look at the occurrence as a function of semi-major axis and as a function of stellar mass? So here we start again from some older work we did. So here Kepler results. All these occurrences are intrinsic occurrence, so all the bias. And the different colors are for different stellar spectral type ranges and therefore different average stellar masses. And when you look at this plot, what you see is the similarity essentially of these curves. So you can shift them vertically and horizontally, and then you can even better see how similar they look. So at that time, what we asked, the question we asked is, what is the scaling as a function of stellar mass to have this turnover match for all these different type of stars? And what we found is that that location in semi-major axis where there is the turnover in the occurrence rate, or if you want, this plateau, scales with the mass of the central star to 1/3. So that's interesting because then you can connect it to the inner edges of protoplanetary disk. And we know there are two of them. There is the gas inner edge closer in and the dust inner edge further out. And if you go through the properties of these edges, you can see that that scaling relation up there is the same as the scaling of the co-rotation radius, which is related to the gas inner edge. And the co-rotation radius, as the name says, is the radius where the angular speed of the star is equal to the angular speed of the disk. So now, fast forwarding 10 years, you can now do different and improved, if you want, analysis of this data set. So still Kepler, but you can couple it with Gaia, so better stellar information, and also with LaMOST, and so you can couple it with the stellar metallicities. So in this newer paper, the authors have corrected for stellar metallicity, and they focus on the location of the turnover here as a function of stellar mass, but for the innermost planet in the multi-planet system. And what they find is that the relationship is steeper than what we got by looking at the average occurrence rate. And so overall, these types of studies together, they tell us that the disk inner edge shape this planetary architecture in possibly two ways. One, by concentrating the solids at the dust inner edge, and also by slowing down or even blocking the migration of the planets or all the building blocks of them to the gas inner edge. Okay, so far, again, we have grouped the small planet together. These are plots for planet radii between 1 and 4 Earth radii. But we know that planets come mostly in two sizes. So this is a beautiful result from the California Kepler survey, showing that planets come in these two beams, the sub-Neptune, sorry, here, and then the super Earth here, mostly in this other beam. There has been a lot of literature in trying to understand, is this a result of evolution, or rather the result of formation? So here I'm going to show just one example of a theoretical paper that shows the outcome of both scenarios. So on the top is results from the case of evolution. So in that case, your super Earth would be the stripped cores of the sub-Neptunes. So sub-Neptunes would have the gaseous atmosphere, and then with time, that would have been lost. On the bottom, in the second scenario, is the scenario of formation. So in that case, the rocky planets, so here the super Earths, would have formed mostly as rocky planets after the disk dispersed its gas. So there is an interesting prediction here from these models, and is that this radius valley that you see here would shift towards smaller planets at larger orbital period if you would be in the evolution scenario, so in the case of atmospheric loss. Because as you move out in orbital period, then you have fewer photons that can strip the atmospheres. The opposite, in terms of the location of the valley as a function of period, would happen in the case of planet formation, because outward you would have more solids to form your planets, and so you could form larger planets. So again, there is a lot of literature here. This is one of the latest results where you can find also references to previous work. And the conclusion from this particular paper is that post-formation atmospheric mass loss seems to shape mostly this radius valley, because you see that the radius valley decreases towards a longer orbital period. Yes, so I would also encourage you to look at the presentation from Yves Lee, because there was some additional information on how formation can partly shape this radius valley, and also there are posters on that. But now, another way you can look at this problem is again by using the stellar mass as a leverage to have some information. So what you see here is also from Kepler, intrinsic occurrence as a function of orbital period, and now we have divided the super Earths, which are in green, from the sub-Neptunes, which are in blue. And when you look at this plot, there is an interesting period here where the two occurrence rates are equal. Inside that, the super Earths are more numerous. Outside that, the sub-Neptunes are more numerous. So now you can do this type of plots as a function of stellar mass, and you can ask the question, how is this period of equal abundance changing as a function of stellar mass? If you do that, that's what you would find, is that the period moves outward. So one way to interpret these results is still in the context of atmospheric mass loss. This has important implications. Here I'm just listing two of them. The first one I cannot discuss because I don't have time. I just have 1 minute. But if you want, you can ask me later. It's important for when you try to extrapolate into the habitable zone and figure out eta Earth. The second one is that you would expect more young sub-Neptunes and Neptune-sized planets around exactly, young stars. And so there has been now a growing literature using K2 and also TESS in looking at these demographics. So because of time constraints, I'm only going to show you one plot, which however summarizes the work of also other groups in relation to young exoplanets. So now what you see here is the occurrence as a function of age of young subneptunes and subneptunes together. These are all transiting exoplanets, so they are a short period. There is a lot of information here, so let me tell you where to focus. First of all, there is the bin of the old planets, and if you want the subneptunes and Neptunes, you should be looking at this point down here. And there is another region that we cannot cover yet. This is where there are still disks between 1 and 10 million years. And then what we notice is that in general, the younger stars have more of these subneptunes and Neptunes as expected through the evaporation. I see that the chair is already here, so I cannot talk about future results, but I leave you here with some, at least the final slide, and then I'm happy to take questions. Thank you.